Hello everybody, I'm back with a few more videos on common gate amplifiers. Today we're going to be discussing a more generalized gain equation for the common gate topology. Excuse me. Last time we saw the last lecture we saw the old structure where we have a very simple one where we had drain resistance. Um, Pretty simple, right? The signal source was coupled to the source of the MOSFET, and I know I've said that the voltage source is coupled through a capacitor, but this is just for representation, nothing much. And the gain we got from here was GM times 1 plus eta times RD. Right. What we're going to do today is we're going to look into a new, um, or rather a more accurate structure, where we consider channel length modulation, the output impedance, and also of the MOSFET, and also the an impedance of the signal source, basically, right? Because it's connected to the source, we're calling it RS for now. Right. So let's go ahead and derive the gain equation for this, and we can work from there. Okay. All right. Let's first do the small signal model as usual. So I think by now this is clear to everybody. Also, I want to mention something after I do this. Hold on. Let me first finish. It's about small signal models, and I know I haven't been very descriptive previously, but we all evolve, right? So, are not GMB VBS, and we have a V out here and an RD here, right? Now, there's a small change in this small signal model if you compare it to the ones that we've seen in common source amplifiers, as in the R out here, R out here is generally hooked up to this place. Have you seen that before? But here in this common gate amplifier, we have it inside this parallel structure. Why? Because R out is connected between the drain and the source, yes, but the source is not grounded as it is grounded in a common source amplifier, right? So we have to note that change, right? Nothing much, it's pretty simple. So, alright, so this is the small signal model. Let's go ahead and derive a few equations and then we can get to gain from there, right? Let's first see how much current passes through this RS here, right? The way I like to see it is like this. This is V in. This is just my own little understanding of the problem. It doesn't have to be what you think of it, right? You can so we have two current sources here, and then we have V out and we have RD here, right? So how I like to think of it is the current flowing through this is going to go like this and out here, right? So the current flowing through here is the same as the current flowing through RD. And what is the current flowing through RD? It's just V out over RD, right? So the same current flows through RS as well. So we have, and this is, look at this voltage source. Based on that, we know that the current can flow. Let's just assume the current is flowing that direction, right? And the value is V out over RD. Okay, now let me grab a different color. And look at this part now. Doesn't form a loop, so we can apply the Kirchhoff's voltage law. This problem, I mean, this, not the problem, but this concept of doing the generalized gain equation is pretty tedious, I would say. So you hopefully you're writing down with me, because it'll become difficult to we might all get lost at some point of time. It took me a really long time to understand this concept first, because before I could make the video. Alright, so from this loop, what do we have? So since the current is flowing here, we can say that the plus and minuses are here, the voltage drop across here. Looks like this, right? So we can write, if we come from here to here, like this. what can we say? Plus to negative, so that's minus V1. Negative to positive, that's plus. It's a build up in voltage. So V out over RD times RS, right? Current times resistance is the voltage there. And then again, from positive to negative, this is a drop, so this is negative V in equals 0, right? We can just flip the negative sign so that the voltage just have the positive there. So V1 minus V out over RD times RS plus V in equals 0. There's nothing big to this, right? If you've written it with me, it's very simple to understand, right? Okay. Now for the bigger equation, there's another loop we have to consider. Now look at this part now. We're going to be considering the right hand side of this part, right? Well, oh, I didn't see this. I've drawn a resistance for a current source. I'm so sorry. So sorry about that. Hope you didn't copy that down directly. Please change that. It's a current source there. Sorry. Okay, so if you look at the right part of this circuit, let's first figure out how much current is passing through this resistance here. Okay, and how do we get there? Wow, it's becoming very messy there, isn't it? Okay, let's draw that again. So we have two current sources here. This is RO, and here, see this. The line I've drawn here is the current coming from RS. Okay, like this, right here. Okay, and we know that is V out by RD, right? Okay, so let's say V out over RD is the current flowing into this node, and another current flowing from here called GMV1, and another current flowing from here called GMBV1. Now here, if you see, I interchange GMBVBS and GMBV1, and why is that? Again, pretty simple. See, VBS is the bulk to source voltage, but then the bulk is grounded, right? And if you see the source, basically it's the same thing connected here. Do you see this? Here again, the gate is grounded, so GS is basically V1. So we can say that the source is at V1. Get that? Pretty simple, right? See here, the gate is grounded. So let me do this here. VGS equals VG minus VS equals 0 minus VS. So minus VS equals V1, right? So VS equals minus V1. Just for analysis. And here if you see VBS, VB minus VS, and again bulk is grounded, so 0 minus VS minus VS should be equal to V1, because VS equals minus V1, right? So just for analysis, nothing big about it. Okay, so all right, now since all the currents are coming into this node, I'm going to consider a fourth current through RO to go into this node. Now remember one more thing, all this explanation on this video and on books is all reverse engineered, right? The way they assume things when explaining things are because they want a neat looking answer. Okay, so that's why the assumptions happen in the first place. So I'm assuming a current passing into, going into this node, right? So what should it be? The addition, the sum of all currents into a node should be 0, right? From Kirchhoff's current law, or junction law as it's called sometimes. So let's call this current just I for now. Okay, I plus GMV1 plus GMBV1 plus V out over RD equals 0, right? So what is I? I equals negative of V out over RD. um, plus GM V1 plus GMB V1. I've taken the negative outside. Okay, let's remember this very nicely. So this is equation 2. All right. Now, if you go back to this small signal model, right? I'm basically going to be interested. See, these current sources are just going to be giving me currents. That's all I'm interested in, and I've got those currents. Now, all I'm interested in is this path right here, right? The one that the blue thing traces. Let me draw that again. That blue path. So we have V in here, and we have RS here, and we have R naught here, and we have V out, and this is RD, right? I'm just shortening the small signal model so that it's simpler for us to understand. And we said that the current flowing through RS was going in that direction, so we gave it these this sign convention. And for RO, we considered um, a current going down. That means in this it should be going this way. Again, all these are just assumptions. Just don't worry about it. All we're concerned is about how to derive the equation. Okay, so things might seem a bit wayward, but don't worry. Again, if you see this equation when you have a negative sign, you know that the thing you assumed was wrong. I mean, just the opposite direction, right? But again, we do all this just to have a neat looking final equation. So they're reverse engineered, right? So don't break your head over it. All right, let's use the Kirchhoff's voltage law and see what we get here. Okay, so we have V out, and then this goes from positive to negative, so it's a drop, right? So negative of R naught times I, whatever current there is, we just derived that value. And then here you're going from negative to positive, so it's a voltage increase, so that's a positive thing. RS times the current through this is V out over RD, right? And then here again you're going from positive to negative, right? So that's a drop. Minus V in equals 0. Okay. Now here, let's rearrange this. V out equals V in minus RS times V out over RD, and then plus RO times I. Now we're going to substitute the value of I from the top. Okay? Now generally I keep my videos short, try to keep them within 15 minutes, but if this increases, it doesn't really matter because I don't want to break the thread by making a part 2. Okay? Alright, so V out equals V in minus RS times V out over RD plus RO times negative V out over RD negative GM V1 negative GM B V1. Okay, that was big. Okay, so let's call this equation 3. Now if you go back to equation 1, right? Where is it? Okay, here. So we can write V1 equals V out over RD times RS minus V in. Why we do this is basically if the final equation we want everything in terms of V out and V in, right? Because that's our goal, to get V out over V in. So the only thing we don't need here is V1. So we're going to substitute that value in place of V1. Okay, oops, we're out of paper. Okay, let's go here. So if you're writing with me, you won't have difficulty following. So V out equals, okay, I myself lost track there. Okay, we have V in minus V out over RD times RS. And then what do we have? we have plus R naught times negative V out over RD, negative GM plus GMB. I just took GM and GMB together because they both have V1 there. Okay? And then we're substituting the value of V1, which is V out RS over RD minus V in. That is big, isn't it? Okay. All right, let's go ahead and solve this further. All we have to do is just take the V out terms to one side and keep the V in terms on one side. All right. So I need your help here. So this thing can go here. So can this thing. And so can this thing. All right. Let's take a different color. V out plus V out RS over RD. So this is done. And we can bring this out, right? So this is negative here, so when it goes there, it'll be positive. So V out R naught over RD. That's done. And this one, the whole big term, right? So we have plus GMB R naught. Don't forget R naught is multiplying there. V out RS over RD. Wow, that was big. Right? This is the left hand side. We're bringing all the V out terms onto that side, okay? And here on the right hand side, let's put V in and rest of the V in terms. I think there's not much anyways. V in plus we have V in plus, let's see, this is okay, R naught GM plus GMB V in. Is that right? Is this what you've got? Hopefully yes. I think I've not missed any terms. Okay. All right. So let's factor out. See, you have RD on everything, on all the terms here, so we can as well put an RD here, right? So on the left hand side we can do. Let's see. We can pull out V out over RD as we can factor out that. So in you will get what? You get just RD plus RS plus R naught plus GM plus GMB R naught times RS. Is that right? Okay, let's put this square parentheses here. Sorry, square brackets here. Okay, equals, let's factor out V in from here. V in 1 plus RO times GM plus GMB. Okay, alright, I'm going slightly slow because I just don't want to make any mistakes on this one. Alright, I think we can even factor out RS here, but we'll take care of that later. So what we need is V out over V in, right? Okay, so let's do that right away. V out over V in. I'm going to take RD to that side, right? So we have 1 plus RO times GM plus GMB times RD over this entire thing, right? We have RS plus RO plus, oh, that is RD, sorry. RD plus RO plus RS 1 plus GM plus GMB times RO. Woohoo! We found it. We found it. That's it. That's all it is. Well, that's a lot, actually. Right, so this is the generalized gain equation for a common gate amplifier. Okay, so what'll happen, uh, hope this is, I mean, yeah, this is D, right? So hopefully I've not written wrong. Um, so what'll happen is this is a generalized equation. Now what'll happen when you have problems, you might be, they might ask you to ignore R naught, or they might say something is infinite, so they might say something is zero. So all you have to do is just plug in those values and finally get the answer, right? So isn't this simple? I mean, I'm so sorry, it is not simple to derive this, but once you get this, right, you can write it down. You don't have to memorize it. Once you get this, from here, doing problems will become simple. Now, since I claim that, we can go ahead and solve another problem. I'll make another video of that, using this very equation and solving it. Okay, so we'll do that right away. So I would strongly recommend going through this video once again. And I'm sorry if I got stuck in here and there, because it is a big equation, and just practice this once or twice. And one more thing, remember, just for this equation to look neat and clean, I mean, without any negative signs and this and that, is the sole reason for us to assume currents when we do them. Okay, so not a big deal. Just this. Okay, the basic idea is just to use Kirchhoff's voltage law and solve the small signal model. All right, great, perfect. I will make another video of a problem using exactly this equation right away. Okay, all right, see ya. Bye bye.